Okay, this is going to be our fifth video in our magnetic fields and magnetic forces series. In this video we're going to be looking at all the content from section 27.7. This is going to be force and torque on current loops. And so we'll get started here. We're going to start by looking at a rectangular shaped current loop. Okay, so we're going to have some images of these down here, which we'll take a look at. So we can kind of represent this loop as a series of line segments, right? For these rectangles, it's going to be like four line segments all stuck together to form the rectangle that we're looking at. And we can see that because of the way that these forces are exerted on these different line segments, that the overall force on the current loop is going to be zero, right? And we can see that from the sort of diagram A here on the left. We can see that we have a force sort of pushing in this direction, one pulling in that direction, one going this way and one going that way. If you add them all up, we end up with no net force on our loop. But we do end up with a non-zero net torque acting on the loop, right? We end up with a torque that's kind of trying to turn this thing around this sort of axis here, right? Around this sort of in this direction around this axis. So if we look at the images below here, we can see that our rectangular loop has side lengths A and B, right? And this vector mu, this Greek letter mu, over here is a vector that's perpendicular to the plane of the loop. So you can imagine a plane that this loop would sit in. This mu points directly out of the plane. Very similar to what our sort of area vector does when we're looking at surfaces, right? And so we're going to see that this mu, which ends up being called our magnetic dipole moment, and we're going to talk about that a little bit more in a second, is really, I mean, part of what makes it up is the area vector. So we're going to see that they're really very, very similar, right? I should also mention that this angle theta is the angle between this magnetic dipole moment and the magnetic field. Okay, so phi, I should say, is the angle between B and mu. Okay. And maybe the last thing I should mention is that these current loops are kind of idealized, right? So we would normally either have other wires leading to these where we would be generating this current, right? Or there'd be some sort of a source embedded in the wire here or something. But in this case, we've kind of cleaned it all up, and we're just looking at this sort of just the loop to kind of get a simple idea of what's going on here. In these two other images, in figures B and C, we can see sort of if we turn this thing about this axis, well, what the forces kind of look like. So we see when it's turned this way, where it's 90 degrees between B and mu, we end up with only forces that are causing a torque, and no forces that are sort of canceled out along the axis of rotation here. And if it lays in such a way that mu is parallel to B, well, then we end up with again everything canceling out perfectly, and in this case there would not even be any torque, right? So let's keep sort of looking at this. We're going to look at the magnitude of these forces, because that's going to help us sort of come to a better understanding of what these torques are going to be. And so we have the magnitude of these forces, the magnitude of the force F. The force F is the force acting in the sort of positive and negative x direction here. It's going to be equal to IAB, where A is this the length of this side, I is our current running around the wire, and B is the magnitude of our magnetic field, right? And this F prime is going to be equal to IB or IBB cos phi, okay? And so that's the magnitude of this force acting in the positive and negative y directions. Okay. If we added up all of these forces for any sort of loop in a uniform magnetic field, we would find that as we said before, the net force on the current loop in this magnetic field is 0, but the torque is not going to be 0. So if we're rusty on what torques are or how to work with torques, this would be a good time to go back and review them. But I'm just going to sort of jump right into it here. If we remember our definition for torque, it's just going to be the force times the length, or the sort of distance at which this force is being applied from whatever sort of point of rotation we're looking at, right? So in this case, we can just substitute in for F, okay? And substituting in for F, it's kind of an unfortunate sort of notation here. I've kind of chosen to write down FL, but this F is not the same as this F. We're going to be substituting in two copies of this F into the equation here eventually. Okay, so first what we're going to look at is replacing L. Okay, and so replacing L is really just B over 2, right? The L is this length from our axis of rotation to where the force is being applied along this branch of length A here. So this is going to be our length, B over 2, and we really end up with 2 copies of F. 2 copies of F because we have, why is this not working? Okay, there we go. Because we have 1 F in this direction and 1 F in this direction. So really we have sort of 2 forces torquing sort of on this loop, right? So 2 F's, and our length is B over 2. But F, well, I guess first we can cancel these 2's, right? So the 2's cancel, and then the F is really IAB, right? This F here we just talked about is really IAB, which we could calculate using the stuff about magnetic forces on current carrying straight wires that we talked about in the previous video, right? So if we substitute in this expression for our F and we clean things up, we end up with this expression here. But we can go even further, because really AB, these are just our 2 side lengths. A times B is just the area of the loop, right? It's just the area of this whole loop. So we can substitute in for that, and if we do that, we end up with the expression that we see here. This is 27.23 from the text. This is the magnitude of the magnetic torque on a current loop, and we can see here that this is tau like usual. This is our current. This is the magnitude of our magnetic field. This is the area of the loop, and this is the angle between the normal to the loop and our field direction. And again, the normal to the loop is this mu vector, which looks very much like our area vector normally would, and we're going to kind of connect this to the area vector right now. Okay, so we kind of give the product of the area of the loop and I, our current running around the loop, we give this product the symbol mu, okay, and we call this mu the magnetic dipole moment. Okay, the magnetic dipole moment is actually a vector quantity. It's going to have the magnitude IA, but it's going to point in the direction that our area vector would normally point. But let's remember that our area vector, when we're not talking about a closed surface, has this sort of ambiguity. Which direction does it point? Does it point this way, or does it point sort of downward and into the page here? It kind of points. It can point in either direction. But in the case of a magnetic dipole moment, we have a sort of firm definition where we're forced by our conventions to make it point in the same direction every time, and the way we determine that direction is with another right-hand rule. Okay, so you can imagine this would be our usual area vector coming out of our surface here, which is now the area of our loop. Now this area vector is going to be scaled by I, right? Because mu is IA, so assuming I is greater than 1, it'll be a little bit longer. And our right-hand rule is going to determine which direction this thing is pointing. So it's not a situation where it could point back in this direction. It can only point in this one direction, and that's because of the right-hand rule. And the way it works is we have to put our right hand in this loop. We curl our fingers of our right hand in the direction that the current would be running around the loop, and then our thumb points in the direction that our magnetic dipole moment has to point. Okay. So having sorted out all this stuff about the magnetic dipole moment, we can rewrite the equation that we have up here by simply grouping up our I and our A into mu, and so we end up with this expression here. Okay. But expression 4 here kind of, again, looks very much like it wants to turn into a cross product, right? We have something times the sine of the angle between them. And that's really basically just going to end up giving us a cross product. And this is good because when we talked about electric dipole moments back in chapter 21 or whatever, we ended up defining them in terms of a cross product, and the same thing happens here. Our vector magnetic torque on our current loop can be defined as a vector, and really usually will be most useful to define as a vector, and it's just going to be equal to our magnetic dipole moment crossed into our magnetic field. All these are vector quantities. Okay, and as I said, so this is very much like the expression that we generated for the electric torque on an electric dipole in chapter 21, right? This mu would have just been a P, and this B would have just been an E, right? We would have been dealing with the electric field and the electric dipole moment, not the magnetic dipole moment. Okay, so we now have this sort of concept of torque on our current loop, right? And like we did in chapter 21, we can define a potential energy for here our magnetic dipole in a magnetic field, where in chapter 21 we looked at an electric dipole in an electric field. Okay, so the magnetic field does work on this magnetic dipole as it changes orientation in the magnetic field, right? And as this thing goes through an infinitesimal displacement d phi, an infinitesimal amount of work dw is done on it, and this dw is actually equal to the torque times that d phi. Okay, that's the work that's done on the current loop, or I guess on one tiny little part of the current loop. But if you were to integrate over it on the entire current loop, as it rotates through that tiny angle d phi, and really we have to be careful because the integration would be done not over the loop but over this change in the angle. Okay, and so this work done, this work done on the loop by the magnetic field corresponds to a change in the potential energy that this thing would have. Okay, and all of this follows very similarly to the work that we did in chapter 21, so we kind of skip right to the punchline here. As we did in chapter 21 for our torque on an electric dipole in an electric field, we defined a potential energy for that, which is given by this expression here. We're going to do the same thing here, define a potential energy for our magnetic dipole now. So this is going to be the potential energy for our magnetic dipole in a magnetic field, and it's simply going to be given by the negative of our magnetic dipole dotted into our magnetic field. Okay, so that's just a sort of value for our potential energy for this dipole in the magnetic field. Okay, so let's take a look at magnetic torque on loops and coils. Okay, so we looked at sort of a simple example where we built our loop out of 4 straight segments of wire, but these equations that we originally built for these rectangular shapes are actually going to apply to any planar loop. And so what's meant by a planar loop? Well, a planar loop is basically any loop that you can lay flat on a table, right? So this thing has some shape in 2 dimensions, but it isn't like bumpy in a 3rd dimension, right? So this thing, if you laid this flat on a table, it would lay flat. No part of it would sort of stand up, right? You can embed this thing in a sheet, in a plane, and that's why we call it a planar loop. So for any planar loop, all the equations that we just talked about are going to apply, because for any planar loop, you can approximate it well by just drawing a large number of very, very small rectangles. And then this is the same sort of integration idea, right? We can build any shape out of a bunch of very, very small rectangles, and we can approximate it arbitrarily well if we allow ourselves to get to very, very small rectangles and use lots of these rectangles, right? So we can build basically any shape, and that's what this image is sort of showing us here. We can see we have a bunch of rectangles, which is already a pretty good approximation for the sort of yellowish shape that we have there. And if we wanted to do better, we could just, slice it up more and more and add more and more rectangles until we were arbitrarily close. And then in the limit where we had infinitely many of these infinitesimally small rectangles, it would be a basically perfect approximation for our planar loop here. Okay, so all of the relationships that we built above for our current loops are going to apply to any shape of planar loop, and all we have to do is just take our magnetic dipole moment. It's again going to be equal to our current, and we just need to know what the area of this shape is, and then we can find the direction that the area vector is going to point in, and so we'll know the direction of our magnetic dipole moment. Okay. We can also generalize these equations to a coil of these planar loops, right? So we can think of stacking tons of these loops on top of each other, and if we have, let's say, n very tightly packed planar loops, so we could stack, dozens or hundreds of these on top of each other, and if we did that, all we would really need to do is just count the contributions from each one. But that really just amounts to multiplying our result by n, because we're just getting one result per loop. If we have n loops, we take our result and just multiply it by n, right? And so one example of a sort of situation where you have a bunch of these planar loops all stacked on top of each other is this example of a solenoid, right? A solenoid is just really a sort of helical winding of this wire around a central cylindrical shape, right? So if you tightly wind this wire in your solenoid, you end up with this sort of stack of wire, right? And you can sort of think of each of these as a single loop, right? And it's just laying in a plane which is at a right angle to your axis of your solenoid, right? So you just think of all these planes basically being stacked on top of each other, building up this solenoid, right? And so for a solenoid with n windings, you simply end up with a mu that has a magnitude of n times Ia, right? Because mu before was Ia, but we just have n of them now, so we just multiply by n. And again, our mu, our magnetic dipole moment, is simply going to point, just like it would for any one of these surfaces, sort of following the right-hand rule. You can kind of imagine grabbing this solenoid with your right hand. Your fingers are curling around in the direction of these purple current arrows, and your thumb points in the direction of the magnetic dipole moment. This is the same as it would be for any one of these loops, but now you just have a whole bunch of them, right? You have n of them, and so your mu becomes Nia. And for this reason, that we're basically just multiplying by n, all the equations still work. We just go through, and we can use all the equations, but our mu is just now, instead of Ia, it's Nia. Okay, so we're going to do two sort of examples here. I've stuck them both together. It's not a very long example, and then after this we have a couple more things to talk about in this video, and then we'll wrap it up. So this is example 27.9 and example 27.10 from the text. They kind of use the same setup, and they just look at two different parts of it in both problems, so I just combined it together. We have magnetic torque on a circular coil, and then we have the potential energy of a coil in a magnetic field. Okay? Excuse me. And so let's get started here. We have a circular coil which is 0.05 meters in radius with 30 turns of wire. So we have 30 sort of loops in here. We're going to have our n is going to be equal to 30, right? This winding of wire lies in a horizontal plane. Okay, so you can imagine it's laying in a horizontal plane, sort of flat on the ground. I'm going to draw this in a second. And the coil is in a uniform 1.2 Tesla magnetic field directed toward the right. Okay, so we'll imagine that it's sort of lying down flat. Maybe I'll just draw it right away. So we can imagine like we have. I don't really want to have to put a coordinate system in here because it'll clutter things up. But you can imagine that you have like these coils of wire going around 30 times, kind of like this. And then you can imagine, so this is meant to be sort of sitting in a plane, and then we have some magnetic field like this going to the right. Okay, so this is supposed to be our magnetic field. Because the wire is coiled like this, we can kind of imagine that we have current whipping around this thing like this. Let's say this will be our current, and then so we could use our right hand rule to sort of set up our magnetic dipole moment like this, right? This thing's going to have some radius. We have numbers for all these, so we're going to have radius is equal to 0.05 meters. Our I is equal to 5 amps. Right, so counterclockwise as viewed from above. Okay, and what else do we have? We have our angle between our mu and our magnetic field. It's a right angle. We could have called it phi. Phi would be 90 degrees in this case. Okay, the magnitude of our magnetic field is going to be 1.2 Tesla, and we have an n. Right, we have 30 coils, so our n is going to be 30. Okay. And so for the first part of the question, we have a couple of things we want to answer. We want to find the magnitudes of the magnetic moment and the torque on the coil. Okay, so we'll just write down a couple of quick expressions here. We know that the magnitude of our magnetic dipole moment, or magnetic moment as they call it here, is going to be equal to NIA, right? We know that our torque is going to be equal to the. We could write this as a cross product, but we don't need to because we know what the angle is here, and so we can more easily sort of write it like this, right? And so this is just the magnitude of our magnetic dipole moment, the magnitude of our magnetic field, and the angle between them, right, or the sign of the angle between them. And then A here, A is just the area of our coil, right? The area that it kind of traces out, or if you were to shade it all in, right? So our area is actually going to be pi r squared. Okay, and so to begin with, we just want to find what mu is, what the magnitude of our magnetic moment is. So we can just write this in. Mu is going to be Ni. Well, it would have been A, but it'll be pi r squared. Substitute in numbers for that right away. We know what N is. We know what I is. We know what pi is, and we know what r is. Do that calculation, and you will find a mu equal to 1.18 amp meters squared. Okay, so that is the magnitude of our magnetic dipole moment. Then we're asked to find the magnitude of the torque on this thing. So we can simply take a look at our expression for torque here, the expression that we would have gotten directly out of this expression here, right? Except that we kind of put in our mu here. So basically it's equation 4. And I mean, stopping anywhere along the way here, depending on what you're given in the problem, any of these versions can be useful, right? So we just grab the one that's most useful to us at the time. And so this is basically what we have here. We just calculated what mu was, so we can simply write down tau is equal to mu b sine phi, but this is just going to be 1.18 times 1.2, right? That's the magnitude of our magnetic field, times the sine of 90 degrees. Well, sine of 90 degrees is just 1. And so if you do that calculation, you will find a tau, magnitude of our torque on this thing, is going to be equal to 1.41 Newton meters. Okay, that's our tau. Okay, and that answers the sort of first part of the question, which is the 27.9 part of the question. And then in the 27.10 part, we're talking about the potential energy of this thing. So the question asks us if the coil in the example that we just did here rotates from its initial orientation, like we have it set up here, to one in which the magnetic moment, our mu, is pointing in the direction of B. So we can imagine this thing rotates 90 degrees like this, and our mu and B are both pointing in this direction. What is the change in the potential energy, right? So we're looking for the change in the potential energy. Well, the change in the potential energy, our delta U, is simply going to be equal to our U final, or our U2, minus our U1, or our U initial, right? And using the expression that we wrote down just above here for our potential energy associated to a magnetic dipole in a magnetic field, we can just write down what U2 and U1 are. So U2 will simply be minus mu B cos phi 2, okay? And this is just taking the cross product and considering the dot product and considering the angle between the two of them, right? And then it's going to be minus mu B cos phi 1, okay? We can simplify this a little bit. This is going to end up being minus mu B, and we're going to have a cos phi 2 minus cos phi 1. And then it's just a matter of substituting in numbers, right? We know what mu is, 1.18. We know what B is, 1.2. We're looking at cos of phi 2. Well, phi 2 is what's going to happen when our thing has already flipped over, when our coil has flipped over. And so we have our mu pointing in the same direction as B, and so phi 2 is just 0 degrees. And phi 1 was the way it was originally, where it was at 90 degrees, right? But the cos of 90 degrees is 0, and the cos of 0 degrees is 1, okay? So we just simply have to remember to keep this minus sign in here, and we just multiply 1 by 1.2 by 1.18, and we're going to end up finding a delta U equal to minus 1.41 joules, okay? And that is the change in potential energy. So what is this saying? Well, this is saying we lose potential energy, right? In this configuration, we had some potential energy associated to our magnetic dipole in our magnetic field, and after it flips over and mu is pointing in the direction of B, we no longer have that potential energy. We've lost this amount of potential energy. And I almost ended the video there, but then I remembered that we do have a couple of other things to talk about. So let's think about magnetic dipoles in non-uniform magnetic fields. Everything that we talked about before this point in this video has been magnetic dipoles in uniform magnetic fields. But what if we're in a non-uniform magnetic field? Well, if we're in this non-uniform magnetic field, our current loops are going to have non-zero forces acting on them, right? In the uniform magnetic field, all these forces kind of conspire to cancel out perfectly. But in this case, where we have a non-uniform magnetic field, we can see the magnetic field is not just a bunch of straight lines, but it's kind of curving as we leave our permanent magnet here. We're going to end up with non-zero net force on these loops. Now, when I first looked at this, I guess I couldn't really see the perspective in the drawing, so it like super confused me because I thought the textbook had made an error. I thought that this side of the loop was the close side to us, and this side was the far side, right? But it's not. You can kind of see that the blue line is meant to kind of go in front of this thing and behind the one on top of it. And so make sure you're looking at it that way, because otherwise the right-hand rule doesn't work here and the whole thing breaks down. But if it's actually the case that this is what's closest to us and this part is what's farthest from us, then you can apply the right-hand rule following the current that they have defined here. You can see that the mu is pointing in the correct direction and the whole thing works out. So if you do that, you use the right-hand rule for this, and then you also use the right-hand rule for the force experienced by a current in a magnetic field, right? You can kind of just think about your hand, your right hand, going over the top of this this sort of current loop, and then, I mean, you're going to kind of have to contort a little bit, but you can place your fingers in the direction of I as it goes over the top, and then try to curl your fingers in the direction of B, but B kind of turns out a tiny little bit, so your hand is going to have to rotate ever so slightly more than it would have had to if it was sort of a straight line, and it ends up giving you this force that points just a tiny bit away from the permanent magnet, right? And so that's going to be the same on the bottom part. You're going to get sort of these two canceling out, except there's a little bit of leftover force pointing to the right. And then as you come to these portions sort of in the middle of the diagram, you're going to see if you have your hand pointing in the direction of the current, and you're going to have to do this a little bit carefully here. You're going to have to kind of like put your right hand such that it's running on the front of this thing here, right? Running in the direction of the current, and then you try to curl your fingers in the direction of the magnetic field, right? You're going to end up with your thumb pointing outward in the direction here of this force, right? And so, long story short, if you add up all these net forces, a lot of it kind of cancels out, but there is a leftover net force pushing us away from this north pole of this permanent magnet. If we do the same thing, but now we flip the magnet around and we have the south pole, well, all of our magnetic field lines change direction, and so we're kind of doing the exact opposite thing, and we end up picking up a net force to the left here. And you can kind of, if you have the time and you want to kind of take a look at it, think about the way that this I cross B is going to work going all the way around the loop, and you're going to see that you're going to end up with these tiny little contributions as you go around the loop, all pointing in the direction toward our permanent magnet, and this is what's going to make this thing, slowly accelerate in toward our permanent magnet. Okay. So we kind of needed this idea. I mean, this is a very useful idea, and we will revisit this in the future. But we kind of needed that idea to talk about how dipoles and how magnets work, right? So we kind of can use this idea to build up the idea of why these permanent magnets attract or repel each other, and why they attract non-magnetized, say, iron or other magnetizable materials, right? So we kind of want to think a little bit about a solenoid and a bar magnet, right? So if we think about a solenoid and a bar magnet, the magnetic field are for both of these are kind of similar, right? Or at least the way they orient themselves to the magnetic fields that they might be sitting in are kind of similar, right? They're both going to try to point themselves in such a way that they're lined up with the magnetic field that they're sitting in, right? So for a bar magnet, it's going to be to sort of turn its pole so that the north pole is pointing in the direction that the magnetic field is running. In the case of a solenoid, it's trying to line its central axis up with the magnetic field. Okay, and so to sort of build up this idea, we're going to have to sort of use an analogy here. It's an inexact analogy. To do a full sort of treatment of ferromagnetism, which is basically these sort of permanent magnets, to look at the way these permanent magnets work, we would need to introduce some ideas in quantum mechanics, and that's kind of beyond the scope of this course. But we can think of it through this sort of inexact analogy where we think about electrons as actually just spinning balls of charge, right? So if you think of an electron as a spinning ball of charge, in some senses it's kind of like a current, right? It's like there's charge moving because the ball is spinning and it's charged, and so you can think of it a little bit like a current. These tiny, tiny little currents that would be making up, say, your atoms, and then your atoms would then make up the material that you're looking at. But in the case of iron, let's say, so you have a bar magnet being made of iron. We have these spinning electrons. These spinning electrons kind of act like a current, as we said, and in an iron atom, the magnetic moments of these electrons tend to align themselves in such a way that you have a non-zero overall magnetic moment for your atom, right? So you have these non-zero tiny magnetic moments making up your whole bar magnet. But it's not a magnet yet, right? Let's say you have them all pointing in random directions, and I'm going to use this image below to help out. You start off with a chunk of iron, and you can imagine that each of these arrows is meant to represent the magnetic moment of a single iron atom, right? So they're going to be all pointing, and obviously they'd be much smaller than this or whatever, but they'd be pointing all over the place here originally. But let's say you took a powerful magnetic field and you put your chunk of iron in that powerful magnetic field such that the magnetic field forced all of these tiny little atomic magnetic moments to line up, okay? If they all line up, then all the electrons are kind of spinning in the same direction, and all the atoms have these magnetic moments that are all nicely lined up, and you end up with your magnetic moments looking like this. Well, this now becomes a permanent magnet. You add up all these little magnetic moments, and you end up with a sort of macroscopic and overall large-scale magnetic dipole moment that we can signify with mu here. And it's really this mu that leads us to the way that this bar magnet acts, right? So we end up with this mu. We now have this bar magnet that's producing its own magnetic field, right? And if we were to put this bar magnet in some sort of external magnetic field, the mu would have a torque on it, right? And it would try to align itself with the magnetic field, right? And so we're kind of halfway there now. We have why the bar magnet produces a magnetic field around it, but still, why does it attract other magnets or repel them, depending on how the poles are facing, to or away from it, right? And for that, we just have to go back. We just have to go back to this picture of our current loops. Each of these current loops can be thought of in terms of a bar magnet, right? If you replace this current loop with a bar magnet such that its magnetic dipole moment pointed in the same direction, right? So if you put, so in this case, because your magnetic dipole moment is pointing in this direction, and our loop kind of looks like this. This would be the same as replacing it with a bar magnet with our north pole here and our south pole there, right? That's what this magnetic dipole moment means. Well, if we take a bar magnet with its north pole here and its south pole here, and we try to move it closer, we're going to have a net force pushing it away, right? Like poles repel each other, and so our bar magnet is going to tend to move in this direction. If, however, we then take the same bar magnet, same orientation, like this, north and south, because we still have the same magnetic dipole moment here, and we try to move it closer to our south pole, well, we end up with a net force in this direction, right? Exactly what we would expect to find if we thought of our bar magnets as these current loops, okay? And so I guess I'll leave these bar magnets in here, but this is really for the discussion below, right? So this is for the discussion below. And so that's kind of why we have bar magnets attracting each other when they have opposite poles, and repelling each other when they have like poles, right? Because we have magnetic dipole moments set up such that they're going to interact with a magnetic field produced by that bar magnet in either a repulsive or attractive way, okay? And the last thing I want to discuss for this video is just this quick last little diagram. Why is it then that magnets always attract, let's say, iron nails, like we have in the image here, any sort of iron object which is not even magnetized, right? So what happens in that case is we bring the nail into close proximity with the magnet. The magnetic field produced by the permanent magnet induces this magnetic dipole moment in the metal object, the nail in this case. So because we have a magnetic field that's kind of pointing out like this, it ends up inducing a magnetic dipole moment pointing in the direction that we see here. And because of this, we end up with an attractive force, right? Because the dipole moment is pointing in that direction, which is the opposite of what we saw here in the case of north, right? So if we had a dipole moment pointing in this direction, that would be the same as having a south pole on this side and a north pole on this side, and so we would have an attractive force. That's why we have an attractive force down here, because we have it pointing this way, right? And it's set up this way because our magnetic field lines are pointing in that direction. In the case of the south pole, our magnetic field lines are pointing inward. We induce a magnetic dipole moment pointing inward in this metal nail, right? This iron nail, and so again we have an attractive force, and so the nail is attracted to the south pole. Okay. And so that's all I wanted to talk about in this video. We have a couple of loose ends that I think I'll be able to tie up in one more video for this section. I know it's a long section, but that's just the nature of the material for this chapter. So I'll leave this here, and we'll pick it up in the next video.